Hey everyone, and welcome back to our electronics tutorial series. My name is Aaron from AX Electronic, and today we are still working with op amps. So today what we're actually going to tackle is something really cool that you can do with op amps. So we did say before that they are a high gain differential amplifier. If you remember that transfer function, it often causes your signals to saturate. So if you have more than just a couple of millivolts on your input, your output's going to saturate, and that's not really good for you because you don't want to lose those artifacts, or you don't want to have those different artifacts in your signal. You don't want your signal to clip at the top. So what I'm going to show you today is how we can use these op amps as actual usable amplifiers. So we're going to talk about some of the amplifier rules, the analysis rules, and how we can design them to do exactly what it is that we want. So let's go ahead and get started. So first thing we need to tackle is our op amp amplifier rules. So number one, and this is a pretty important one, amplifiers should have negative feedback. Negative feedback. Okay, so what does that mean? We haven't really talked about feedback or anything like that. So what that means is that our output needs to have some sort of path. It doesn't have to be a short circuit, but it does need to have some path through some components. It could be resistors, capacitors, inductors, all sorts of things, but it does need to have a path through back to our negative input terminal. Okay, so it's important. It has to be negative. Okay. So what this is going to do is that this is going to kind of keep our amplifier stable. So it's going to make sure that we don't start doing all sorts of crazy stuff. It's going to keep our amplifier stable. So if you see something that has negative feedback, odds are it's going to be an amplifier. Now, second rule, and this is another important one to remember, because we have this negative feedback, our output is always going to try to make our negative input equal our positive input. And I'll give you an example for that, okay? So let's start off with an example. And let's say that we have a 1 volt input here, and we start off with 0 volts on our negative input. So what our output's going to do is that our output is going to go immediately to VDD. It's going to try to go to VDD as high as possible because now it's working as a comparator. But what happens is that some of this signal is going to go back through our negative feedback. It's going to come back to this negative part. Okay, so it's going to come back to our negative terminal. Now instead of 0 volts, we're going to have maybe something that's closer to VDD. So what's going to happen is that it's going to stabilize whenever this input reaches the same value as our plus terminal. Okay, so it's going to stabilize whenever it reaches this same value. So that's just a little brief example. If it doesn't make sense, it'll make a little bit more sense here later on, especially once we start the analysis and design rules and stuff like that. So brief explanation is that if V plus is greater than V minus, the outputs will go high until they're equal, and that's where it's going to stabilize at. So that's just something to keep in the back of your mind. So from step 2, we're going to assume at the very beginning that V plus is equal to V minus, and then start solving that way. That's not always a true assumption, but it's a pretty good place to start whenever you're analyzing these amplifiers. We're also going to assume that the output's not saturated, because if it is saturated, then we're going to have a couple more problems. Okay, so we're going to assume our output's not saturated. And we're also going to assume that there's no current into the inputs because, like I said before, these inputs have a super high input resistance. So very little current flows. So it's almost like it's an open circuit and there's actually nothing there. So we're going to assume that there's no current flowing into either of these inputs. Okay? So let's go ahead and jump right in and get started with our first amplifier. All right. So a couple of things that you need to notice here is that we have our input voltage here. Could be any sort of input. Okay, it could be a DC input voltage, it could be a sinusoid, it could be all sorts of different waveforms. Doesn't really matter too much for us right now. All we know is that we have Vin. We also have these two resistors, Rn and Rf. Make sure you can still see that Rf. So Rf we're going to call our feedback resistor, and Rn is our input resistor. Now, rule number 1 is that we have to have negative feedback, and we can see that from our output we have a path to our negative input. So good, we have negative feedback. Rule number 2, we have to make sure that V plus is equal to V minus. Okay, so we're going to assume that V plus is equal to V minus. So we know that these two, we're going to assume they're equal, but do we know what this V minus is at the very beginning? Answer's no. So we don't know what that V minus is at the very beginning, but we do know what V plus is. So V plus is tied directly to ground, so V plus has to be 0 volts. So V plus is 0 volts. Now we know that our amplifier is going to work hard in order to make V minus equal V plus. So we're going to assume that here, this is also 0 volts. Remember, this is just an assumption. It doesn't have to be true, but it's a good assumption whenever you're analyzing these amplifiers. Now we can actually start analyzing this a little bit using some of our circuits analysis knowledge. So we know right here we have Vn because we're connected to Vn. So we know we have Vn here and 0 volts. Now, if we have a voltage drop across this resistor, what's going to start flowing? Current. That's exactly right. So we're going to start having current flowing through that resistor. So I'm going to go ahead and call this I1. Okay, and that's just going to help us later whenever we're doing a whole bunch of different math. It's going to help us keep our stuff straight. So I'm going to call this I1. So let's try and calculate I1. So from Ohm's law, we know that current is equal to voltage drop over resistance. Now, what is our voltage drop across this resistor? Well, in this direction, it's going to be Vn minus what's on the other side, which is 0 volts. So instead of having minus 0, anything minus 0 is just itself. So I'm just going to do Vn over Rn. All right, so that's I1. We know what I1 is. So this current flowing through this resistor is equal to Vn minus 0 over Rn. Great, so that's our first step. Now, if you remember from our circuits analysis series, we know that there is a law called Kirchhoff's current law. And that tells us that whatever current flows into a node has to come out of a node. So it's like we can't just create electrons out of thin air. So whatever goes in also has to come out. So there's no current flowing into this input terminal. That was rule number 5, okay? So no current into the inputs. So whatever current is flowing in here also has to come out this way. So let's call this I2. Now, I2, we can also calculate. So we know that this is V out. We're just going to call this V out because we're not 100% sure what it is, but we know that it's V out. So if we look at this I2, in this direction, our voltage drop, we start with 0 volts and then minus V out. Okay, so in this direction of current, it's starting with 0 volts and following the direction of the current minus V out. So our voltage drop is 0 minus V out over our resistor here, which is just RF. So I'm going to simplify this a little bit. I'm going to say minus V out over RF is equal to I2. Now, like we said before, this I1 has to be equal to I2 because there's no other path for that current to flow. So we know that I1 equals I2. All right, so let's set these two equal down here. So let's say our I1 is Vn over Rn, and our I2 is minus V out over Rf. Now we can cross multiply, and then we end up getting Vn Rf is equal to minus V out Rn. We're almost done here. So last thing, let's divide both sides by minus Rn. And what we get is that V out is equal to Vn times minus Rf over Rn. Okay, so we know what our input is, or at least we know where it's coming from. So for example, if it's the output of a guitar or an electric guitar, something like that, it's going to be this little tiny signal that we want to amplify. So we know what our input is, and now we can figure out that our output is equal to this input times the ratio of these two resistors. The important thing is there's a negative here. So if we take just one more step and we divide both sides by Vn, okay, so that's what we're going to do. We're going to divide both sides by Vn. And what that's going to give us is V out over Vn is equal to minus Rf over Rn. Okay, so V out over Vn, that's the ratio of our output to input. Okay, so that's kind of like our gain. So this amplifier is going to have some sort of gain or attenuation. And if we want a large gain, then we need to make sure that this ratio of these two resistors is also large. And like we said before, there is this negative sign here. So if we have a positive input, that's going to give us a negative output, okay? So this is something super important to remember, that we have this inverting amplifier. So that's what this one is called, inverting amplifier. So let's say that we have some signal coming out of a guitar. Okay, so we have some signal coming out of a guitar. I'm going to erase some of this math over here that we want to amplify by 10 times. Okay, so we want to amplify this signal by 10 times. We can actually use this inverting amplifier to do that. Okay, so we know that our V out over V in, we want that to be equal to 10. So we want our V out to be 10 times greater than our V in. We can design for this pretty easily. Okay, so if we make our Rn something simple, so let's say that our Rn is 1 kilo ohms. If we pick our Rf to be 10 kilo ohms, then our ratio, Rf over Rn, remember there's a negative sign there, is going to be minus 10. So we're getting 10 times greater signal, it's just flipped upside down. Okay, so it's flipped across the x-axis. So whatever's positive is negative, whatever was negative is now positive. Okay, so this is our very simplest amplifier that we can make with these op amps. And this is kind of how we analyze it. We start by assuming that the two ports are equal, and then we start using these Ohm's law. We know Ohm's law, and we can get these currents, and we can set those currents equal to each other because we know that there has to be the same path between these two. We can use that to make this very simple amplifier. Now, let's look at a little bit of a different configuration. Okay, so this first configuration, we started off with this input going into our negative terminal, right? And we didn't have anything on our positive. We just had our positive as 0 volts. Now we have our input going into our positive terminal. We still have this Rn and we have this Rf. Okay, so we have Rn and we have Rf. So it looks very similar. The only difference is that our input is now going to our positive. Okay, so let's think about this the same way we did the previous problem. So we started off by saying that we know this positive voltage is 0 volts. The only thing that's different is that we know that this one is now V in, right? So whatever our input signal is going directly to this positive terminal. Now, rule 2 or rule 3 is that we assume that V in or V plus and V minus are equal. So we are going to assume that this is also V in. All right, so we're going to assume that that is V in. Now we know that this is 0 volts down here, and we know that this is V out. So following those same steps, we can analyze this problem and get that gain, get that transfer function. Okay, so let's try and do that. So let's start off by calculating. This current here. And I changed the directions because I think it's just a little bit easier, makes a little bit more sense for me. So let's call this one I1. So we'll say I1 is equal to Vn minus 0 volts. I'm just going to get rid of that minus 0 over Rn. Okay, so I1 is equal to Vn over Rn. Now let's calculate I2. So with the benefit of hindsight, we know that we're going to try and set I1 equal to I2. So we need to make sure that they're going the same direction because we know that there's no current flowing into here. So whatever I2 is, I1 has to be equal. Now I2, we can use Ohm's law again. If we do V out minus V in, because that's the direction of the voltage drop through this resistor since we're going to the left, over Rf. Okay, so this is our I1 and I2, and if we set these two equal to each other, that is going to give us Vn over Rn is equal to V out minus Vn over Rf. Okay, now I'm not going to do all the math here because it'd get pretty boring just watching me do this algebra, but at this point it is just an algebra problem. So you can solve for this, and what you end up getting is that V out over Vn is equal to 1 plus Rf over Rn. So it looks very, very similar except for this 1. Okay, so we have a 1 here, and we also don't have a negative. We do not have that negative here anymore. So we are only positive. So because we don't have that negative, that means that if we have a positive input, it's also going to be a positive output. And if we have a negative input, it's also going to be a negative output. So instead of an inverting amplifier, this one is called a non-inverting amplifier because engineers are very descriptive. So if it's an inverting amplifier and it inverts, and one that doesn't invert is going to be a non-inverting amplifier. So something to note about this one is that our gain, or our V out over V in, is always greater than 1 because this Rf over Rn is always positive. You can't have negative resistors. So this is always going to be greater than 1. So we can only have gain. So only have gain. Now what does that mean? So let's look at this previous configuration. Okay, so let's say that we have a really, really big signal. So we have a really, really big input signal and we want to drop it down. Maybe we have a signal that goes 0 to 10 volts peak to peak, and we want to read it with something like an Arduino that can only read up to 5 volts. So we want to drop that down. we can use an inverting amplifier to do that. So if we pick, let me change colors. Oops. So if we pick RF and RN in a smart way, we can actually make it to where this provides attenuation, or the opposite of gain. It makes our signal smaller. So let's say that I pick RF is equal to 1 kilo ohm, and now Rn is equal to 10 kilo ohms. So now it's backwards. So if Rn is equal to 10 kilo ohms, our gain, or V out over Vn, is going to be equal to 1K over 10K. So now our output signal is going to be 1/10 of what our input signal is. So this one lets us provide attenuation, or lets us drop our input signal down. This non-inverting amplifier doesn't let us do that. So we can only have gain. So if our RF is 0, which is the smallest we can possibly get, then we're going to have a V out over Vn of just 1. So it's just going to pass straight through. Nothing's going to change about it. So we can only provide gain with this amplifier. We can't drop a signal down. So we can actually expand the inverting amplifier a little bit, and I'll show you guys how. So this looks a whole lot like our inverting amplifier. I'm going to switch back to red. So switch back to red. We know that we start off with 0 volts here, and because we want our inputs to be equal, we're going to start off with 0 volts here as well. So we have this I1, I'll call this I1, and I2 now. So we have 2 inputs here. So we have these 2 inputs. And then let's go ahead and call this one I3. Okay, so this is our node right here. So we have I1 going in, I2 going in, and I3 going out. So this one's going to be a little bit different, which we'll see later. Let's go ahead and start off by calculating our I1 and our I2. Okay, so I1, this one's pretty simple, is just Vn1 over Rn1. Okay, if you're a little bit confused about that, go back and look at what we did previously. I skipped a couple of steps. Namely, I didn't write out this Vn1 minus 0 volts. Okay, I2 is very similar, so it's going to be Vn2 over Rn2. And then I3, it's going to look pretty much exactly like our output current from our inverting amplifier. So before, our output current was I2 right here, and this is going to look very similar. So I'm going to do it over here. Say I3, and it's equal to negative V out over RF. All right, so now we're going to apply Kirchhoff's current law, except now we have 2 currents going in and 1 current going out. So that means that I1 plus I2 has to equal I3. So let's write that out and see. So we have Vn1 over Rn1 is not equal to, plus Vn2 over Rn2 is equal to V out over RF. All right, so now let's solve this a little bit. Make sure I put this Rn2. Okay, so let's do a little bit of manipulation on this. So what we can do is that we can see, let's see here. So what we can do is that we can see that our V out with just one step is equal to RF over Rn1 times Vn1. Okay, so that is by multiplying this RF here. Now we still have this that we need to deal with, so we're going to do plus RF over Rn2 times Vn2. Now what does this look like? Well, now our output voltage is proportional to our input voltage plus our second input voltage. So we have these 2 input voltages, and this is like we're adding them together. Oh, I did forget something though. So this is a minus V out. This is going to be minus RF and minus RF here. So this is an expansion of the inverting amplifier called an inverting summer. So inverting summer, that means it's summing up our input voltages, and you can see that. So we have our Vn1 plus Vn2. Okay? And all that is changing them is this RF and Rn1, RF and Rn2. Okay, so you can actually weigh these 2. So if maybe you want 10 times more Vn1 than you do Vn2, you can make Rn1 10 times smaller. Okay, so make Rn2 10 times larger. You can work this math out to just kind of see, but the only thing you need to take away from this is that we can actually sum these 2 signals together by using this configuration. So let's look at a simple example. If RF, Rn1, and Rn2 are all equal, so let's say they're all 1 kilo ohm. So this simplifies to -1 This also simplifies to -1. So now we get V out is equal to minus VN1 plus minus VN2. Okay? So this is a good example of an inverting summer. You can also weigh those inputs. So maybe if you need one input more than the other, you can weigh them. Okay, so do you remember back in our first op-amp video when I said that you don't necessarily have to have the plus and minus supply? You can get away just fine with using a 10-volt supply and ground, okay? So you do require a little bit of a different configuration. So if we just forget about this capacitor here, if we assume that this capacitor is just a short circuit, then this is going to look a whole lot like our inverting amplifier, okay? So this looks a whole lot like our inverting amplifier. So why did I add this capacitor here? So let's go back and let's assume that this capacitor is not here and we have an inverting amplifier. So let's say that I have a sinusoidal input like this, okay? So it goes positive and it goes negative and it's oscillating around 0 volts, okay? Well, at this very beginning, whenever this is positive, this inverting amplifier is going to amplify it and try and make this output go negative, right? So it's like amplifying it, trying to make it go negative. Let's also assume we don't have this capacitor here. Okay, so this is going to try and make its output go negative. But we're bound by these rails. Remember, we can't go beyond these rails. So our lower limit is 0 volts or ground. So we can't do this. So we're just going to be stuck at 0 volts, and then we're going to amplify this other part and be stuck at 0 volts, amplify this other part, stuck at 0 volts. So we're losing a lot of information in our signal. Now, a way we can actually get away with that is by using these capacitors, okay? So if you remember, capacitors are like DC open circuits. So like DC open circuits, but they will let AC pass through. So the higher frequency that you have on AC signals, the more they're going to pass through. Okay, so if we assume that we have a high frequency sinusoid, like maybe a 1 kilohertz sinusoid, we can actually analyze this problem a little bit differently. So let's start off looking only at DC signals. So this has no DC signals. So this is like 0 volts DC. It's only a sinusoid. So we can put 5 volts here. We know that it's going to try and make 5 volts there as well. And at DC, this is going to be like an open circuit. So no current is flowing at all. So that capacitor charges up, and it's going to provide us a nice 5 volt jump here. Okay, so this capacitor is providing a nice 5 volt boost for us. Okay, after it's charged, it's going to have 5 volts charged up across it. And now, if we look at our AC signal, we may have our input signal of, let's say here we have maybe 1 volt or something like that. So we're going to have 1 volt. This is going to go through our N1, and then it's also going to get its voltage boosted by this 5 volt signal here. Okay, so now instead of 5 volts here, we're going to try and make it to where it has, or excuse me, so instead of 5 volts here, we're going to have this nice 5 volt drop across this capacitor, and that actually lets this work with just a single supply. So this is like adding a DC offset to our input, okay? So even though this input is oscillating around 0 volts, if we take a look over here at our negative input terminal, here, it's actually oscillating around 5 volts. So it's giving it a nice little boost. That way it can work how it's supposed to, okay? So it's like adding a DC offset to where we're working right in the middle of these two supplies. Now, there is some unfortunate side effects, namely low frequency response. So if you try and work with a DC signal here, it's just not going to work. Or a low frequency signal, it's not going to work, because these capacitors are going to start working like open circuits and blocking that signal. But this is a nice little solution if you maybe need just a single supply amp, but it does take a little bit more analysis. I just wanted to give you a brief little introduction to this, and what I'd encourage you to do if you're still a little bit confused is actually plug this into LT Spice. Do some AC circuit simulation or some transient simulation and just kind of probe around to get a real feel for this circuit, because it's going to work a whole lot better than just you listening to me. You need to do these problems if you're going to really understand these electronics. All right, so let's look at just one more special case, okay? So let's look at one last special case. Now we have our VN here, and this VN can be anything. We're back to having our dual supplies, so we don't have to worry about that old capacitor problem that we had. So we have our VN here, and we do have a path from output to negative, okay? So we do have a path from output to negative, except now there's no resistors or anything like that. So it's a little bit simpler. So let's start our analysis. We know that this is going to be VN, because that's what we're applying to this terminal. And we know that this amplifier is going to try and make it to where there is VN right here as well. And the best way for it to do that is to just make V out equal to VN. So V out is equal to VN. So this is in a special case that's called a buffer. Okay, so this is a buffer, or like an amplifier with a gain of 1. So it's just going to pass whatever's on our input directly to the output. You might be wondering why we do something like this. And the reason is because if you have maybe an input that is really sensitive to its load, like maybe it can't provide a whole lot of current, this is providing 0 current at all. So it's not really having an impact on our signal. But on the output, this has a really low resistance path. Okay, so it's a really low resistance path, and it can provide a little bit more current than our input. Okay, so this is like a good way of protecting our input signal, making sure that it doesn't change too much whenever it gets loaded down by whatever's on the output or whatever's downstream. Okay, so this is the last thing I had for you on our topic of amplifiers. If you do have questions, it's definitely understandable. Please ask them in the comments below, and I can either point you in the right direction or give you some resources that you might need to understand these problems a little bit better. If you did enjoy this content, please give me a thumbs up and subscribe. Like I've said before, it keeps me extremely motivated and very happy to keep producing more content. Other than that, if you guys don't have any questions, I will see you next time.